Alrighty, today we are going to take a little time, maybe today and tomorrow, to look at the graphs of sine and cosine. Now, in the past, when we started talking about the unit circle, I briefly showed you, what the graphs look like. But today we're going to learn about all the different parts and the behaviors and everything like that. So the one thing I want you to remember is that both of these functions are what we call periodic, right? So as we travel around the circle, right, once we complete one full rotation, after that first rotation, we're just repeating everything that we did, right? So that's called periodic because we periodically return to our starting point or whatever point that we're looking at. Okay, so that's one of the main big catches of our two functions. So I'm going to graph them out here for you, and then we'll dissect them a little bit. We'll take a look. All right, so for today, we have our x and our y, or sometimes, this might be theta over here. But what we're going to do is we're going to break up our divisions. No, let me make that smaller. Our x values are going to be in radians. All right, so we have the 4 units there, okay, that correspond to 90 degrees, 180 degrees, 270, and 360. Because usually that's what we consider as one period. So for the sine function, the sine of 0 is 0. So the sine function, we say, starts at the origin. Now, taking into consideration that we use the unit circle, okay, and from what we learned, the range is from -1 to +1, right, for both the sine and cosine. So unless I manipulate my function otherwise, and we'll see some examples of that, we won't go above +1 and we won't go below -1. So at 90 degrees, or at pi over 2, the value of sine is 1. At pi, or at 180 degrees, the value of sine is 0. At 270, or at 3 pi over 2, we're down at -1. And at 2 pi, we return back to 0. Right? So, and then we connect the dots with this curved line. Right? And that's the basic sine function. Right? Now it just doesn't stop and end here, right? It'll keep doing this. And pretty much what we can do is we can copy and paste this forever, okay, in both directions. Right? So here, for both of these, but for now, for this one, from 0 to 2 pi, okay, we're going to call that the period, right? Because that's one full rotation. Now, I may have mentioned this before. Be careful. Even though I come up and I return to 0 here, this isn't one period because I didn't go through the whole motion. I didn't go through all of my values, right? So it has to do one full, we call this a crest. It does one crest and then a valley, right, when it dips like this. And then it returns back to 0. All right, so from 0 to 360, we have one period. All right. Similarly, we have the same thing for cosine, but cosine has a different starting position. Cosine of 0 starts up at +1. Then from +1, we go to 0 at pi/2. At pi, we're down at -1. At 3 pi/2, we're back to 0. And then at 2 pi, we return up to 1. Now this one is a little more clearer with the period because we can see it starts at the top and then it returns back to the top, right? But again, it's the same period of 2 pi, right? And like we said, the range for both of them is between -1 and +1. All right, any questions so far? Right, so again, this would just be sine of x or sine of theta. This would be the cosine of x or cosine of theta. All right, so that's the very basic parts of it. Now, obviously, like any other function, we can manipulate what this graph looks like. All right. Obviously, we're not just dealing with just sine and cosine. We've seen, sine squared or 5 sine or sine of theta over 2. All right. There's a bunch of things that we can do to the sine function, and that will change how the graph looks. So first we have what's called the common form. Now they're both essentially the same. And for now, I'm going to use x instead of theta. All right, so we have 4 parts here. All right, and they are the same for both sine and cosine. So today we're going to look at 2 of the parts, the A and the B. We'll do it in alphabetical order. So the A has a special name. A is what we call the amplitude of our trig function. All right, so what the amplitude does is it affects our range. Okay, so actually real quick, let's take a look at some examples. So first, let's just look at the sine of x, right? So here, the maximum here is even nice. It gives us in radians, 2 pi at 1 is our maximum. We start at 0. Here we're at pi0, -1, and then back to 0. If I multiply in the front, it kind of acts like it does when we saw in algebra if I multiplied x squared, right? If I multiply by a large number, it kind of stretches it out vertically, right? It makes it taller or skinnier. So if I did, I'll do it down here so we can compare 2 sine of x, right? What I just did was I just changed the amplitude. The amplitude is now 2. Right? So now notice, I didn't change the period, right? It still has the maximum in the same spot. It still crosses the x-axis. It still has the same zeros. It still has the minimum in the same spot. But now it goes higher. It goes up to 2. It goes down to -2. Right? If I make it really tall, right? If I have 5 sine, again, it does the same thing. I could even go in the other direction. I could say half sine of x, right? And that gives kind of this more shallow sine function. Now, we have to be careful. Okay, by definition, the amplitude isn't the whole thing. Amplitude isn't the range. Okay, the amplitude represents half the distance between the minimum and the maximum. So if I'm looking at my original functions, the amplitude only goes from the origin up to the top. Right? Or the origin, the x-axis, down to the bottom. Okay, the amplitude isn't the full range. Right? And when we take the amplitude, we're not worried about negative numbers, so we take the absolute value of a. Actually, real quick, let me show you what happens when we have a negative. You might be able to guess. I'll leave the 2x up there. If I did -2 sine x, okay, remember when we have a negative in front of our function, it's a reflection. Right? So again, I still have the same period. But now, instead of starting off going up like this blue line, like 2x, 2 sine of x, I start going down. I reflect over the x-axis. Right? So these two, if I'm just talking about the amplitude, they have the same amplitude of 2. It goes from the middle up to the maximum. Okay, and in our case, our middle is the x-axis, y equals 0. Right? So if you're asked to find the amplitude of a function, you're just going to look at the number in front of the sine or the cosine. Real quick, just to show you, it's all the same with cosine. So if I had my original cosine, and if I do maybe 3 cosine, right, it's the same thing. It's just larger. It's more stretched out. All right. So the amplitude, all it really does is it changes the range. Right? It makes it taller or shorter. And again, we just take the absolute value. So the other part I want to talk to you today is about this b, because this b directly affects our input variable x or theta or whatever we have there.
Wait, Mr. Mayor, can you go back really quickly?
Yeah, sure thing.
All right, thank you.
You're welcome. All right. The term b here helps us determine what the period is. Okay, the b doesn't tell us what the period is directly, but we can use the b there to help us find the period. Now, normally, what we've seen, b is 1, right? Which means if I plug it into here, 2 pi over 1, our period is 2 pi. Very straightforward. So what happens here is, because I'm multiplying the variable that we're plugging in, I just forgot words. Independent variable, right? It's directly affecting that. So if I'm multiplying it by some larger number, that's going to affect the period. That's going to, either make the period shorter or longer, right? And we get this relationship 2 pi over b. So let's take a look at what happens, and we'll compare it to what we see here. All right, so let's do cosine again. So I'm going to leave the original cosine function there so we can see it. So now let's do cosine of 2x. Okay, what happens now is it's like an accordion, and we're kind of pushing it together. Because I'm multiplying it by 2, what happens is it goes through its period at a quicker rate, right? So again, I start at 0, 1, just like my cosine function. But now I complete a full period a lot quicker up here at pi instead of all the way over here at 2 pi, right? Essentially, I halved my period by multiplying by 2. So there we kind of have an inverse relationship. I'm multiplying my independent variable by 2, and that shortens my period by half. Right? So if I make that even skinnier, cosine of, 5x. Right? Now we're really scrunched up together. Right? And I can even go in the opposite direction. I could say the cosine of 1/2 x. Right? And that's going to kind of pull us apart. Now it's taking a longer time for us to complete one period. Right? So now I'd go up, down, and up in twice the amount of time. Right? This would be, 4 pi. Right? So you can see we're taking that 0.5. If I divide 2 pi by 0.5, right, that changes the period. That increases my period. All right? Any questions so far?
No, but I feel like this is really similar to what we did last year. It's kind of like
Okay, yeah, you might. Some of this might be, especially just with the sine and cosine stuff. Right. Yeah, I don't know if you did it in geometry or algebra, but when you talked about like translations and stuff like that, you may have done stuff like this. So yeah, it could be either. I forget if it's geometry or algebra too.
Will b ever be
So,
negative?
That's a good question. No. We're usually going to keep that positive. But that's a good, let's take a look. Let's do some discovery. So I'm going to keep the cosine there. So what happens if I do cosine of negative x? It gives me the same function. Right? But just for comparison, let's just double check with sine of x, sine of negative x. There, it flips it. All right. So when we throw a negative in front of the x and not in front of the whole function, it's a horizontal flip. Right? The reason we didn't see anything with cosine is because that's what we call an even function, right? It's symmetrical. Everything on the right side is an exact image of the left side. So if I reflected it, everything would end up in the same spot. Right? So, but because sine is actually an odd function, right? It's opposite on this side and on this side. When we do that negative part, okay, it does that. So if I did sine of negative 2x, right, I'd still have the same period as sine of positive 2x. Let me get rid of that. It's too much. Right? So all it's doing is it's kind of inverting it. Right? Everything about this, the period is still the same. We treat it the same. And we just worry about the positive number that's next to it. Okay, that's a good question. I don't think I've ever been asked that before. All right. So what I want you to do tonight, I'm going to give you a few functions, and I just want you to find the amplitude and the period. So let's go over one quick example. It's pretty straightforward, especially because the amplitude is so easy. You just literally look at a number. Now, again, what's nice is it doesn't matter if it's the sine or cosine function. They both behave similarly when we're talking about the amplitude and period. All right, so let's find the amplitude and period of y equals negative sine times pi x, or negative sine of pi times x. And then I'll graph it along as well. All right, so the amplitude, I'm just looking at this number out front, and I take the absolute value. So the amplitude is 5. That's all you got to do for amplitude. No math involved. Okay, the period, you're taking the number that's next to the x, next to the variable, but you don't include the variable. Okay, I don't want an x in your period. So it's going to be 2 pi divided by whatever we have here, pi. And now we just simplify. Here the pi's cancel out. And my period is now 2. And that's it. All right, just be careful if this is a fraction. All right, if you had sine of x over 2 like this, all right, here our b would be 1/2. All right, so then when you find the period, that's 2 pi over 1/2, which means we keep, change, flip, and we actually end up with a larger period. And I showed you this one. But real quick, with the last minute we have, let's take a look at negative 5 sine pi over x. All right, so here, my period happens my period is 2, right? So it's not even involving pi anymore. So from 0 to 2, I complete 1 rotation, right? I have the 5 as my amplitude, so that makes it really tall. And this pi here squishes it together. So we have a really skinny and a fast up and down. All right. Any questions?
So B is always going to be in front of X.
Correct.
Well, like
It's always
if it's
going to be,
up like that?
I don't want to say in front of, but it's always going to be the number with X, either multiplied or divide.
All right, thank you.
You're welcome. All right, guys. So keep an eye out. You'll have a few problems like this. You're just going to find me the amplitude and the period, and then we'll go over that tomorrow. All right. Have a good day, everybody.